Good morning. In this lecture, we would like to understand different modeling of diode. Means uh, model of diode for large signal DC input, model of diode for large signal AC input, and model of diode for small signal AC input. Okay. Now you are familiar with the symbols of the diode. Okay, let's start. This is the symbol of diode, and you are familiar with this curve also. Okay, that is this is the curve between I and VD. Okay, now obviously this is an exponential curve. You are familiar with this one. Okay, now the relation between this I and VD is given by this equation. Okay, this is an exponential equation. Obviously this equation is valid in the forward bias in this region only. Okay, now here I is your that diode current, VD is diode voltage, and neta VT is constant number. Okay, VT is called thermal voltage, E is your exponential, and IS is your reverse saturation current. Okay, now this is the actual model. Okay, this is the actual exponential model of the diode. But now the problem with this model is that suppose you want to solve a circuit. Okay, a circuit in which one or two diodes are there and some DC inputs is there, then it is going to be difficult to solve because we solve the circuit on DC using the Ohm's law. Okay, KCL, KVL. Ohm's law is applicable when the element is linear. Linear means between I and V there is this kind of relationship. It should be straight line passing through origin only. Then only your Ohm's law is valid. But here you can see that diode is not a linear element, so your Ohm's law is not valid. So we cannot write the KVL and all these equations. Okay, so now it becomes difficult to solve the diode problems. Okay, so we have to build a model for diode which can be replaced in the DC circuit or in AC circuit, and we can solve the circuits. Okay, basically what we do we again let's go back. The modeling of diode is divided into two parts: large signal model and small signal model. Okay, large signal model means AC or DC input, the voltage or current should be high, large enough. Okay, and in small signal the voltage and current is very small. Okay, we will discuss this separately, don't worry. Okay, let's move to the large signal analysis. Okay, here this is your actual model of the diode, but now we are going to replace it with this model. Okay, this model there is one voltage drop, constant voltage drop, and there is one straight line. Okay, now straight line, so your diode in the forward bias is replaced by an ideal diode, and this much voltage drop, and a resistance with value equal to 1 by slope of this line. Okay, so this is called the large signal model of the diode. Okay, now whenever in a DC circuit, okay, we want to solve the circuit, we can simply replace with this model and then we can solve it. Okay, now this diode is going to behave ideal. Okay, if the voltage across this one is positive, it is going to turn on, and then the current can flow. Okay, now overall we consider this as a diode, this entire diode, but this is your ideal diode. Okay, this is the voltage and this is the resistance. Okay. Now what is the value of this resistance? We can simply calculate the slope of this one, and then we take inverse of this is going to give you the value of resistance. Okay, and this V gamma is this value, this much voltage. Okay, now some special case, if this RD is 0, okay, if this RD is 0, you get constant voltage drop model. Likewise, if your voltage this V gamma is 0, then you got this model, and then if both V gamma and RD is 0, you got the ideal voltage ideal diode model. Okay, So these three models are frequently used in large signal DC analysis. Now same model is applicable for large signal AC analysis. Okay, so you can simply replace in a large signal AC analysis circuit, you can simply replace by this model and then solve the circuit. Okay, so nothing much is there, so it's easier to solve. Okay. Now what are the advantages? Obviously it is easier to solve and it is applicable for both a large signal AC and DC. Okay. Now let's come to the small signal analysis. Okay. Before moving to a small signal analysis model, okay, let's do one exercise. Okay, there is one DC voltage source and there is one diode. Okay, I am talking about ideal diode, and there is one resistance. Okay, now obviously the diode is forward biased, so some current is going to flow. Okay, let's that current be this value, let's call it I only. Okay, now let's I increase. Okay, let's consider that I increase the value of V little bit. Okay, around 0.1% or 0.2% like that. Okay, increase the value of V. Obviously the current is going to increase little bit. Okay, little bit the current is going to increase, and now again I decrease the value of V little bit, 0.2% like this. Okay, the current is going to be like here. Okay, again I do this operation again and again like this one, so you can see that I will get this amount current like this one. Okay, now you can observe one thing, that this source consists of one constant DC component and one variable AC component. Okay, so this diode is not blocking that AC component. We can write this V as equal to VDC, means the component which is constant, plus VAC AC. Okay, now this, because of this some constant current is flowing, because of this there is some fluctuation in the current. Okay, now we can think like that two sources are there. Okay, one source constant DC voltage and one more source fluctuating AC voltage. Okay, now this diode is not blocking that AC component. Why? Because listen this, because it is not blocking, because the AC component is superimposed on DC value. I repeat, the AC component is superimposed on DC value, that's why it is not blocking. Okay, so if this diode is forward biased and there is some positive current is flowing, and in that positive current if you superimpose very small amount of AC, that AC component is, the AC current component of AC current is going to flow without any blockage. Okay, it is not going to block the AC component. Okay, so from that we can understand that diode simply behaves like a short circuit for AC component, but that's not totally true. It is going to offer some resistance. Let's understand how it is going to offer some resistance. Okay, let's understand from this one. This is your actual curve. Okay, now at this point you are operating, let's say at this point you are operating. Okay, at this point basically this is the DC current. Okay, at this point the current is flowing, the DC current. Okay, now in this you are changing the current little bit up and down. Okay, so we can calculate the slope at this point. You will get some slope and take inverse of that slope, that is going to give you one resistance. So that resistance is the resistance offered to the small signal AC current. Okay, I repeat, there is already some DC current is flowing. Okay, and on that you apply some AC current also. The diode is not blocking the AC current, but it is offering some resistance equal to inverse of slope at this point. Okay, at this point of the curve. Okay, so your diode is simply behaving as a resistance for the small signal AC current. Okay, simply resistance, but there is one criteria, one condition, that there must be some positive current is flowing, okay, some DC positive current is flowing, and that AC current is superimposed on DC current, then only this condition is true. If there is no current, then the AC component of current cannot flow. Okay, here the slope is going to be 0, so the if you try to find out the resistance, it comes out to be infinite. Okay, so AC will also get infinite resistance. So AC current can only flow if there already exists some DC current and AC current is superimposed on it. Okay, so now let's calculate that resistance. That resistance is basically slope. Okay, here slope is calculated. Okay, now we can differentiate that earlier equation, exponential equation, and we are going to get this equation. Okay, just differentiate that exponential one, and there is some manipulation. Overall, this is the equation you got for the resistance, that is called dynamic resistance. Okay, neta is again a constant, Vt is constant for a given temperature, and I is your DC current. Okay, so from DC current you are going to calculate the value of Rd. Rd is the resistance offered to the AC current, not DC current. Okay, remember, Rd, this dynamic resistance is the resistance offered to the DC current, AC current, not DC current. Okay, fine. Let's move. Okay, so this much resistance is offered to the AC small signal. Okay, again the same thing is mentioned here. This is only true only if there is some positive current flowing. Okay, so this is the model. Okay, this is the model for the small signal model of the diode. Okay, whenever there is an AC analysis circuit, you are going to replace the diode by this one, provided some positive current is flowing. Okay, now look, while we are doing all this, because we want to apply superposition theorem. Okay, suppose let's understand from this one. Okay, I want to find out this current. Okay, I want to find out this current. Okay, so the current across the diode is equal to sum of this current plus this current. Okay, this side some AC small signal AC voltage is applied, and this side some DC voltage is applied. Okay, now you must know the model of this diode for this small signal. Okay, then only you can solve this circuit. Okay, basically to apply the superposition theorem, you must know the model of the diode. Otherwise, with what model you are going to replace. Okay, so let's understand. Here the same thing is written. Okay, total current is IDC plus IAC. Okay, now let's move to the procedure. Okay, how to solve an diode circuit when both AC and DC voltage are applied. Okay, that's it. First step is to solve the circuit on DC. Means in this kind of circuit, remove the capacitor. Okay, means first you have to solve the circuit on DC. First you have to prepare the circuit for solving on DC. That means you have to remove the capacitor, open circuit the capacitor, and then solve the circuit and find out the value of ID. Okay, and then RD. Once your ID is more than 0, then only you will go for AC analysis. If current is less than 0, then you are not going to get anything. Okay, first find out the value of IDC and then RD also, and check whether ID is more than 0 or not, and then if it is more than 0, then you are allowed to go for the AC analysis. Okay, next, deactivate the DC source. Okay, now we have to make the circuit ready for the AC analysis. For that, deactivate the DC source, means short circuit that voltage source and open circuit the current source. Okay, and then find the IAC, that is find out the IAC through the diode. Okay, now capacitor should be replaced by a short circuit, and diode should be replaced by its dynamic resistance, and then you can find out the value of IAC, and once you have, then you can get the total current. Okay, for example, let's analyze one problem. Here the task is to find out the total current, this current. Okay, this current, this side one AC input voltage is there with this much of value. Okay, this much of frequency, and in this side some DC voltage is there. Okay, now we want to apply the superposition theorem. Okay, first obviously when DC is there, okay, when I analyze the circuit on DC, this capacitor should be open circuited. Okay, so this is the circuit you got. Now you can simply solve this circuit. This is fairly easy. I am considering this diode as ideal for the timing. For the DC, I am considering this ideal. You can replace with other model also if it is mentioned in the question. For the timing, I am considering it ideal for or DC only. Okay, so I find out the IDC current. Now IDC comes out to be positive, so I can go for the calculation of RD. Okay, so this is the equation, and this much value you got for the dynamic resistance. Okay, now we can move to the move for the AC analysis. For AC analysis, simply short circuit this voltage source and short circuit this capacitor. Okay, this is the model you got. Okay, now you can calculate this IAC. Okay, it is a simple equation. So this much current you got. Okay, so the total current comes out to be IDC plus IAC. Okay, so that is how you are going to solve the this kind of problem. Okay, so to summarize, diode is modeled differently in large signal and small signal. In large signal, you have constant voltage drop model along with some resistance. Okay, so this is the model. This is the model for the large signal, and for the small signal, you have only one resistance, that is the dynamic resistance, provided some DC current, positive DC current is flowing on the diode. Okay, so on AC you replace by this one, and then you can simply solve the circuit. It is similar to that of the MOSFET. Okay, in MOSFET you first perform the DC analysis and then you go for the AC analysis. Okay, you first find out the current and all this, okay, and drain current and all this, and then you go for the AC analysis, and then you calculate the voltage gain and all this. But here voltage gain concept is not applicable because this is not an amplifier. Okay, but in MOSFET circuit, in amplifier circuit, there may be some diode. Okay, so you have to replace when you build that AC circuit. Okay, AC circuit, you have to consider the AC model of the diode. Okay, you can simply you cannot simply open circuit or short circuited diode. You have to consider that model also. Okay, thank you. In case you have any question, you can put in the comment section, and you can share this video with your friend. Okay, thank you.